Thank you all for being here today. We have the pleasure to welcome Charlie Paxman, who is a postdoc at GANIL. And if I'm not mistaken, he graduated in the PhD in Surrey, and you will be talking about the work you did during the PhD on shell evolution beyond calcium-48. So Charlie, whenever you want to start, the floor is yours.
Thank you very much. Thank you for inviting me here today to talk about my PhD work, as you said.
Sorry to interrupt. Would it be possible for you to increase your sound volume, because we don't hear you loud enough, I think.
Is that any better?
Sorry, could you repeat?
Is that any better?
Yes, it's better. Thank you very much. Okay, please go on.
Sorry about that. Yes, so thank you for inviting me to talk about my PhD work, which was looking at exotic cross-shell interactions in the region kind of southeast of calcium-48, calcium-48, by looking at DP transfer of potassium-47. First of all, I'm going to give kind of a little bit of background about why we care about nucleus structure, what it is and why we care about it. So the atomic nucleus is a really complex many-body quantum system of non-identical interacting particles. So it's very difficult to describe. And in particular, it's made more difficult by the fact that we don't have a fantastic grasp of the nuclear force that governs its structure. But what we can do is we can simplify this extremely complex object into models of the shell model you can see here, where you can, using this, we can start to actually look at the nuclear structure and have some way of interpreting the results so that we can feed back the structure that we observe to more fully understand the nuclear force and the nuclear object. So the shell model, kind of briefly introduced is a theoretical perspective where you consider the nucleus to be an inert core surrounded by valence nucleons in a manner analogous to the atomic physics. As you can see, this is probably a fairly familiar image to you, where you have the Wood-Saxon potential, where you have the spin orbit interaction, and then you get these magic numbers popping up here, where you have particularly large gaps between nuclear orbitals. And the shell model has been a fantastic tool, and it's been very effective at predicting shells and shell evolution, where as you move away from stability, which of these numbers becomes magic begins to kind of shift and change. However, the shell model does require input from experimentalists in order to understand the interactions between different nuclear orbitals to be able to predict structure like this. So if you were to perform an experiment to get these orbital interactions, it's generally easier to access nuclei that are closer to stability, such as this one here. But this gives you a pretty limited field of view, because the structure that you're looking at will be dominated by interactions between orbitals that are pretty close together. But even in a nucleus like this, that's close to stability, these higher lying orbitals are still pretty significant in the structure of the. They still have some level of influence in the structure, but it may be quite minor, and we don't have any handle on these interactions. But what we can do instead is we can try to look towards more exotic nuclei. So if we add, for example, 14 neutrons to the system here, then the structure of this nucleus is now dominated by the interaction between this S-half proton down here and a P3 half neutron over here. By the way, I'm hoping you guys can see my cursor. Maybe a little clearer. So by looking at structuring exotic nuclei, we can access these missing matrix elements in the nuclear force. But how are we measuring these components experimentally? One of the tools that we can use is direct transfer reactions. I'm going to talk specifically about direct transfer with deuterons. So in a situation like this, you would have your initial nucleus, AX, and a deuteron, and then you perform, for example, DP transfer, where the neutron from the deuteron has now been kind of dropped onto this initial nucleus, and you have a proton still left over here. So one of the advantages of a tool like this is that you have pretty good selectivity on the states you're populating, because you retain some kind of sort of a memory of the initial structure, because you're populating states in this final nucleus that look the most like, in their wave function, the initial nucleus plus a neutron. So even though this is a pretty simplified diagram, it's not that far, it's not that crazy to say that you really are just kind of dropping a neutron onto it and seeing what structures you populate. This means that you suppress the more complex configurations. So you really are looking at the most single particle-like structures in this nucleus rather than the complex collective structures, or those with like very fractured wave functions. Additionally, by performing a transfer like this, you have sensitivity to a lot of information in this nucleus. So for example, the different nuclear orbital that you occupy when you transfer your neutron, in this case, affects the angular distribution of the proton that goes out. So if, for example, you were to populate this green orbital, then your proton has a higher probability of going in different directions. So by observing this angular distribution, you get quite a lot of information about the orbitals that you're occupying. Additionally, from the energy of the proton, you can determine the excitation of your nucleus, and also by the number of protons observed, you can find kind of a relative population strength of all the various states in this final nucleus. And this relative strength is the spectroscopic factor, and by extracting the spectroscopic factor, which is kind of a measure of the wave function overlap, then you can start to learn information about the single particle energies of all of these different nuclear orbitals. So, with a little bit of background onto the actual experiment that was performed for my PhD thesis. So the work that we wanted to do here was looking in this region of calcium-48, kind of southeast, because as you move east, there's some interesting stuff happening where the calcium-52 and calcium-54, there's a growing body of evidence that these two seem to be kind of doubly magic, looking at their first excited 2+ state energies and things like that. So it seems that there's some kind of shell evolution here where 32 and 34 become magic. Additionally, as you move down, there's this, you're moving towards the n=28 island of inversion, which is a region down here where you get increased conductivity in the structure of the nuclei, despite being kind of technically on a magic number. So this magic number begins to weaken as you move down. But the descriptions of nuclei in these regions are limited somewhat by the fact that the interactions that are so critical to the structure here. So, for example, these interactions here, so you've got the S-half proton here and some level of FP neutrons. We don't actually have an experimental constraint on these interactions. So a large section of this quadrant of the nuclear chart is based on interactions that we don't know, we haven't got a handle on. So ideally, what we'd like to do is we'd like to perform a DP transfer of phosphorus 43 here. So we would drop a neutron into one of these FP neutron orbitals up here. We could measure states that result from this interaction, and then we would get a better understanding of these interactions. But unfortunately, there isn't actually a facility currently that can perform this experiment, maybe EFRIB in the coming years, but this has been pretty inaccessible for a long time. What we can do instead, as we did at GANIL, is we can exploit some interesting exotic structure of potassium-47, whereby this is kind of an adapted figure from some collinear laser spectroscopy work that was done at CERN, where you can see that for most potassium isotopes, the proton structure is to have a full S-half orbital and then a hole in the D3 half. Except for a couple of really interesting anomalies here, such as potassium-47, which has a hole in the S-half and a full D3 halves. And that means that it's kind of effectively kind of a facsimile, like a fake of the phosphorus-43 ground state. It's just got this full D3 half on it. So what we can do instead is perform DP transfer here, drop a neutron into these same interesting orbitals up here, and measure the same interaction. So we're looking at these really exotic interactions for the first time using potassium-47 DP transfer. This experiment was performed in 2021 at GANIL using radioactive isotope beam provided by the spiral 1+ complex. It's a pretty good beam. It was 5 × 10⁵ particles per second, and importantly, it was pure because it was reaccelerated using the SEAM cyclotron, which had a sufficient mass resolution to remove all contaminants from the beam. So it had a really pure beam in this experiment. This was then impinged on a thin deuterated carbon target at the center of this circle here, you can see. And the beam itself was monitored using a single CATS detector, multi-wire proportional counter. For those that are familiar with CATS, especially on the Lees line, you may know that they're usually used in pairs, so you can get the trajectory of the beam. But in our case, we had just the one, so we didn't have a handle on the trajectory of the beam, which will become important later. But what it did do for us is it allowed us absolute monitoring of the beam intensity, and it was also provided a timing signal that we used throughout the experiment. In the center here, we had the MUGAST array, which is a transitional phase of the GRIT project, where in the upstream we had 6 trapezoidal GRIT detectors, which are kind of the new style ones that are being developed, and it was coupled to the MUS2 detectors in the downstream and at 90 degrees for the detection of light ejectiles. So you can see here, it's kind of hard to see because of various reflections, so I'll make it a bit easier. We have, these are the trapezoidal detectors of the new style, a MUS DSSD for elastic scattering, and in the not pictured here was the MUS2 telescopes for detection of DT tritons. And we got some full width half maximum out of this, as a pretty nice resolution for particle spectroscopy in the upstream and downstream. And then around this, we have the AGATA array, which is a gamma ray tracking array, one of 2 in the world, I'm sure you probably know. This was used in our case for the detection of prompt gamma ray emissions. So pictured here is some of the AGATA triple clusters. In our case, we had probably about double this. We had 36 crystals positioned 18 centimeters. Pulse shape analysis, an add back of the gamma ray spectroscopy was performed online, and then the results were Doppler corrected in coincidence with light ejectiles detected in MUGAST. And then again, we had a full width half maximum of about 7 kV, 1.8 MeV from this. And then finally in the downstream, we had the VAMOS magnetic spectrometer, which was positioned in a 0-degree arrangement for our case, which meant that it was receiving the full beam intensity. Therefore, these drift chambers and the ionization chambers weren't used. We only had the multi-wire proportional counter, which was sufficient for our case in order to reject reactions on carbon in the target, which is generally a very significant source of background in these types of transfer experiments. So the triple coincidence of the heavy recoil in VAMOS, the light ejectile in MUGAST, and the prompt gamma ray in AGATA was really critical for the success of this experiment, because we're trying to populate states in this odd nucleus, which has a high level of uncertainty. So a little bit of analytical background. I'm not going to go too into detail on this. But looking at the spectrum here, you can see we have the lab energy, so the lighter ejectile detected energy versus lab angle. You can see in the center here, we have the elastic scattering detected in MUS2 of protons and neutrons. And this was pretty critical in order to normalize our results of dP and dt, which are the results we care about. But the normalization comes from here. I'm going to go a little bit into that, so we've got a bit of time. The normalization factor that we apply here, which contains the number of beam particles and the thickness of the target, is the same for each of the 3 reactions that we're looking at here. So by knowing that the beam intensity is monitored absolutely using our single CATS detector, we can determine the target thickness by comparing our elastic scattering results to calculation, as we have here. So we have the deuteron elastic scattering results here, and proton, that is compared to optical potential calculations using Dirac and Fresco. And by this comparison, we can determine quite nicely relatively precisely the target thickness, and therefore extract the normalization factor that is then later applied to all of our direct transfer results. So if we look in the upstream region now, towards the DP detected in the grit trapezoids, this is our experimental focus, and this is where we can observe the neutron orbital vacancies. But it was also quite helpful in our case because, as I mentioned, we didn't have beam tracking, and we knew that we didn't, that the beam wasn't centered on the target during our experiment, which was quite significant because it meant the beam also wasn't centered in our particle array. So as you can see at the top here, each of the different MUGAS detectors had a shift in energy because of the offset of the beam. So in order to correct this, we performed a numerical minimization, varying the X and Y position of the beam on the target, as well as the Z position of the target, and the target thickness within the parameters that were defined by the elastic scattering. And through this numerical minimization, we managed to get a really accurate alignment of the kind of average position of the beam, which you can see was like 4 millimeters off in the X direction. And by doing this, we managed to align each of the detectors quite nicely across the whole range of energies and range of angles. So a little bit about the actual results that we got from here, particularly in the plasticity and focus on these are the spectra that we received. So we have the excitation spectra up here, which is the reconstructed excitation spectrum from protons detected in MUGAS. And you can see each of the states over this point are all new, and we populate states all the way up to the neutron separation energy. And then below that, we have the gamma ray spectrum from AGTA. And here you can see kind of the advantage of having gamma ray spectroscopy because we have this really thin resolution of the gamma rays compared to the particle spectroscopy. So already from this analysis, we can start to see some things. So we can see some decays from excited states directly to the ground state, like this one here. We can see decays to the first excited state and also to the second excited state. But the real kind of strength of this analytical technique is 2D analysis. So here we've got the same spectrum, but kind of projected onto either axis. So we have excitation up here and gamma rays along the way. So by looking at the coincidences in this way, we can determine the excitation energy of each of these states, as we were saying before, to the 7 keV precision of the AGTA gamma ray spectroscopy. But more importantly, we can also isolate states that were unresolved in the particle spectrum. So I've pointed at 2 here, where these 2 states lie on top of each other, or pretty close in the excitation spectrum, but by projecting it along the kind of gamma axis, you've very clearly separated them. I pointed out this region here because it's probably easier to see. I'm hoping on the through the whatever resolution you're getting from the Zoom call. There's also up here a region that may just be about 4 pixels to you, which is kind of where it was more important because up here we have 3 particle states that lie directly on top of each other that we would not have been able to separate out without the gamma rays. But with gamma rays, we can cleanly separate them, which is quite helpful for us. And additionally, the inclusion of the gamma ray spectroscopy means that we can see above the neutron separation threshold, we're actually populating unbound states as well, because there's particle events up here that are in coincidence, pretty clear coincidence with a gamma ray that is not M48, this is in potassium-47 on beam nucleus. So here we're populating a state in potassium-48 that is unbound. It's kicking off a neutron, going back to 47 and then decaying. So we can see that quite clearly with the inclusion of gamma ray spectroscopy. So through this work, we managed to expand the known level scheme of potassium-48 by quite a significant margin, and also find a whole bunch of new gamma rays in this nucleus. So while this is extremely cool and fun, it's not really what we're going for, because what we need is also the spins and the structures of all of these states. So in order to look at that, we need to look at the angular distribution of the detected proton. So here I've got some theoretical differential cross sections, so the amount of counts over the lab angle for a P wave state and an F wave state, so occupying the P3 half or P half orbital or the F5 half orbital. And by comparing these to our experimental results, you can see we get a really unambiguous assignment of whether it's P wave or F wave. So this is the observed counts at each angle corrected for efficiency by the use of realistic geometry simulations and normalized using that figure that we got from the elastic scattering. And then by scaling the experimental and theoretical lines here, we get the spectroscopic factor, which is the measure of the wave function overlap between our final state that we're occupying and the initial state that we started with in potassium-47. So this is kind of this is what we're looking for, is these spectroscopic factors. Kind of a sort of an overview of our results here is that we observed 9 novel states completely, so that's with spin parities and spectroscopic factors, as well as 3 higher energy states up here, for which we managed to get a combined spectroscopic factor, but not individual spin parities. So that the pretty high quality of our results here in differential cross sections allowed us to perform some pretty detailed comparisons with the shell model, which we're going to show in a little bit. And you can see that we also have very clear, distinct regions of P wave states at lower energies and then F wave states at higher energies. And interestingly, we actually have one mixed state, which you can see here is little G in the middle, which is very clearly neither E nor F. So by taking these spectroscopic factors that we've now extracted and adding this to the level scheme picture that we had before, we now have the gamma ray transitions, the L wave of the occupation, and the spectroscopic factors, which gives us a good guess at the state, spin, and parity to start with, and then by comparison to the shell model, we can confirm these further. And then also by comparison to the shell model, we can actually extract the structure in each of these states. So we can't experimentally distinguish between P3 half and P half, but by comparison to the shell model, we can be pretty sure that this is a P half state and this is a P3 half. Very cool. So as we've got quite, we're doing okay for time, I'm also going to talk a little bit about the DT results. So this is going the other direction. So you can see here, this is in the downstream direction. It was kind of a simultaneous data set that we managed to get at the same time. And this is looking at neutron orbital occupation. So we're taking the initial beam nucleus of potassium-47 and we're ripping a neutron out. And this gives us some interesting kind of corollary data with the neutron addition. This was a much more challenging analysis because of it being in the downstream direction means that you have much more background because there's more reactions that will emit something in the downstream direction. So there's more gating requirements that are placed on this. There's also fewer events, and we'll cover a smaller angular range in this region. So this is much less clean data, unfortunately. But this is helped by the fact that potassium-46 is a much more well-known nucleus than potassium-48. So a lot of the states were already known through other experiments. The only one that's new is this one at like 4.2 eV up here, which is a novel state. However, despite the fact that this is already a pretty well-known nucleus, this is the first DT study. So it's the first time that spectroscopic factors for DT transfer into this nucleus will be measured. And it's also the first time that gamma ray spectroscopy has been performed on some of these higher lying states. So we've got quite a few new gamma rays up here as well. So by comparing our experimental results, which you can see here, where the length of the filter bar is a spectroscopic factor, this one's kind of less clean than the potassium-48 one. And because of the more difficult analysis, the choice of L transfer is informed by the known spin parity in the shell model, rather than being extremely clear as it was in the DP. But a couple of interesting things we can note is that the new state at 4.2 is actually mixed. And because it's mixed, it means that we can be sure that the spin parity of the state is 1+, because that's the only spin parity that can result from both S half population and D3 half population. So even though we don't have clear gamma rays from that state, we've still got a nailed down spin parity. There's a couple of other interesting things here, such as the strength of the F7.5 all being in this kind of lower pair of states and none in the higher pair, as the shell model predicts them to be kind of spread around between these 4 - 3 pairs, which is quite interesting. Additionally, the mixing between S half and D3 half disagrees in pretty much every case. But the most important thing that comes out of this work, half character, is not populated very much. It's a very small population, as we were expecting in the shell model, which is good news, because if this was to have an unexpectedly high proportion, an unexpectedly high spectroscopic factor, that would imply that the potassium 47 in its ground state had some greater softness along this N=28 shell closure, so we had more neutrons drifting up into these p and f orbitals that the ones we're trying to look at. So the fact that there's nothing, or it doesn't appear to be any neutrons kind of exciting across this gap work and the implications for the end of inversion requires us to compare our experimental results to some shell model calculations. So 2 shell model calculations were performed for this work using SDPF-MU and SDPF-U. And both of these are kind of like state-of-the-art for this region of the nuclear chart. Both of them have the same valence space, so they're both looking at the same kind of limitations in terms of valence space, and they have the same SD shell interaction as well. They vary in their FP shell interaction, but what is most important for us is that they vary in their cross-orbiting of a transfer in this sort of region. So you could say that the MU is closer to first principles and the U is kind of more empirical. So despite having nearly identical names, the cross-shell interaction of the 2 shell models is of completely different origin. So, I done a slightly complex diagram here, comparing the experimental results with all the states and the spectroscopic factors to the MU calculations and the U calculations. So a few things I just want to kind of pick out here is that neither calculation can account for the mixed state that we observe or the shell model various, because this mixed state could be a decent anchor for the high-lying F5.5 orbital states, because as you can see in both of the calculations, there's a much larger gap between the red and the blue than we see experimentally. So to me, this seems to imply that there's some level of like, spacing issue between 2 that could be resolved by trying to use this kind of anchoring point of the mixed state. Additionally, the spectroscopic factors that we observe experimentally are pretty small compared to what are expected in the shell. So if we take this 1.9 MeV state, for example, you can see that the spectroscopic factor bar is filled kind of just over halfway. But the states that we connect it to in both shell models are nearly full in both cases. So we know from the DT transfer, as we were just saying, that there isn't any unexpected population of these orbitals, so there's not already neutrons there to be blocking population, to be kind of reducing spectroscopic factors in this way. And what we actually expect could be responsible for this is the proton configuration mixing. So I'm going to try and back up that claim a little bit here. So if we take only the simple states, so nothing mixed, and nothing that required like extra levels of analysis, just the simplest, clearest states in both the DP and the DT, and we compare the measured spectroscopic factor to that that's calculated by the shell model, which is on this y-axis here, then we can compare this to this is getting a high concept. Compare this to the fraction of the wave function that the shell model thinks is of this S half whole character. So that is what we're in theory populating, right? It's the character of this S half whole. And you can see that there's this kind of relationship between the two. So for states that have a smaller fraction of S half whole that we would expect to populate less, the shell model is underestimating the spectroscopic factor of these states. whereas it's significantly overestimating those that have a larger fraction of this S half whole component. So this kind of relationship between the two, where we're actually kind of most accurate for states that are around 15% fraction, implies to me that there is, when we don't have a good grasp of the mixing between proton configurations in this region of the nuclear chart, where the different proton orbitals are nearly degenerate. So it's having some influence on the neutron spectroscopic factor that we haven't fully got a handle on yet. So coming back to this figure here, there's a couple of other things we can see, and kind of most strikingly is that the ground state is wrong in both shell model calculations. So you can see here that both shell models expect the 2- state to be the ground state, whereas it's experimentally observed to be 1-. This is something that wasn't new in this work. We already knew that the ground state was wrong from the collinear laser spectroscopy work that I mentioned before. But what is new in this work is that we've observed these two higher lying 1- states for the first time. And this means that we can start to look at what exactly is causing this spacing to be wrong. So we have found that by altering these two specific matrix elements by a magnitude of about 1 MeV, you can increase the spacing of these three 1- states and then correctly reproduce the 1- ground state. So you're kind of pushing them apart. You're pushing this, the lowest 1- state into the ground state position. So you can kind of fix it by looking at these two specific matrix elements. And this is, I mean, it's great for potassium-48 to be able to predict it more accurately, but where this becomes really interesting is if you look at the implications of changing these two matrix elements further down the n = 28 isotopic chain. So if we were to look here at, don't worry too much about what is exactly these lines are. These are the spectroscopic factor, the energies of each of these states weighted by spectroscopic factor. So for example, the orange solid line is the average energy of the 0- states resulting from p-half neutron, and the solid blue are the average of the 2- states resulting from f5-halves. But if you look at the patterns of these average energies from potassium-47 dp at the furthest left to 45 chlorine dp and 43 phosphorus dp, so this is moving down the n = 28 chain, then you can see that the predictions of the two shell models begin to diverge pretty significantly. In particular, the proton orbitals, the neutron p orbitals even, begin to become sort of degenerate in the mu case, whereas they remain fairly separate in u. And if we make these adjustments that we just mentioned to these two specific matrix elements, and we look at how that changes the predictions of phosphorus 44 really in the middle of the island of inversion, you can see that it actually brings these p orbitals even closer together and lying pretty much on top of each other. So it increases the degeneracy in this region. Again, being careful, these are simplistic adjustments made by experimentalists. So a theorist needs to come along and kind of confirm this. But it seems to imply that there's more degeneracy in this region than we're accounting for in our shell models. This could be pretty interesting for the island of inversion because degeneracy in orbitals like this could cause like the increase in collectivity that we're seeing. So it could give some kind of, to nail down the single particle structure that is occurring here to cause the collectivity. So ideally what we would want to do next in this sort of work to confirm this would be to perform this 45 chlorine dp transfer, and then further after that the 43 phosphorus dp transfer. Eventually, someday, we're doing this. So this work constitutes the first experimental measurement of the exotic interaction marked here between an S-half proton hole and the FP neutron interaction orbitals. This was conducted through the use of the potassium-47 dp transfer and additionally dt transfer in the other direction using the Mugast-Agatha-Vamos setup at GANIL. And a whole range of P-wave and F-wave states have been identified through this work, many of them with spin parities and all of them with spectroscopic factors. A pretty detailed comparison with shell model calculations reveals a couple of key markers that will be significant for our understanding of this whole region of the nuclear chart going forward. In particular, the relative energies of the 1- states that we observe in potassium-48 indicate failures in specific matrix elements, and by correcting them, we seem to increase the degeneracy in this island of inversion. Neither shell model can account for the mixed state that we observe, which could be a fun anchor for this really exotic interaction with the F5 half going forward. And additionally, all of the states have this strange relationship between the spectroscopic factor accuracy and the proton configuration, which implies that there may be some failure in our understanding of the mixing between proton configurations in these nuclei. And finally, we would like to continue to clarify this work by performing chlorine-45 dp and phosphorus 43 dp, which may be becoming possible in the near future with improved beams such as those being built at and this talk actually comes at a pretty good time because the physical review letter journal based on the potassium-48 work has just been published this last Friday. So if you want any more details, you can always refer to this paper here. So with that, I'd like to thank you very much for your attention and take any questions.